Talk mesocyclone. Okay. Which one do you want me to go?
16. 16. 9.
Okay, I hear 16 the most. Let me see.
Hey, it's absorbed by the.
Hey, when are you uploading the lecture for Friday?
No, it's thermal
It's up.
or something like
It
that.
is?
Yeah, it was up Sunday.
I was trying to search for it.
And it wasn't
Yeah.
on there.
I
It
didn't
should
see.
be there under like work and energy. There should
Really?
be a playlist of work and energy.
Well, that's why I didn't get the new one done.
I'll look it up if I get it.
Number 8.
Okay, so which one?
16.
16.
16. Okay, so here's the deal. So you got the car moving, right?
Correct.
And
So good.
here's the tree. So the car is going to hit the tree. Is the kinetic energy of the car going to change?
Yeah.
Yes. Is work going to be done on the car? Yes. Does work equal change in kinetic energy?
Yes.
Is change in kinetic energy equals K minus K naught?
Yes.
What's your final kinetic energy? 0. What do you need to find the initial kinetic energy? 1/2 mv squared, right? So you have all the information that you need to find the initial kinetic energy. True?
So if you find the changing energy, you found the work.
You found the work.
Okay.
And then you can set that equal to your course and distance.
So are these answers going to be negative?
They can't be.
Change in kinetic, change in
Well,
energy.
it's just, so you said it can't be negative.
Energy itself can't be negative. But change in kinetic energy can.
And work can be.
And work can be
The
negative.
amount of work and the size of the force.
So here's the deal. If the force is causing the object to do one of two things, either slow down or lower its potential energy. So if you're decreasing any type of energy, potential or kinetic, that's going to be defined as negative work. If you're making something go faster or speed up, where you're increasing the potential energy or making it go faster, that's defined as positive work. Okay?
Was I doing something else right?
Yes.
I didn't know you could
So when you said like
Yeah.
pushing in the front of the car, you just meant like the car hitting the tree?
Yeah.
Okay, that's what I was confused.
Yeah, it's going to
I meant like the person got out of the car and like started pushing, and I was like, why? But okay.
No, that's what happens when it hits the tree.
Okay.
Yeah, the person isn't.
Yeah. Okay.
That has never been an
All right,
issue.
number 8.
It is now.
Okay, let me see.
It's just 2 cars on equal mass.
Okay, 2 cars of unequal mass, da 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 da. So here's the deal. Do they both have the same kinetic energy?
No.
Do they both cars have the same kinetic energy? Are they going to have the same final kinetic energy? Are they going to have the same change in kinetic
All the
energy?
words just kind of mixed together.
Is that change in kinetic energy equal to work?
Yeah.
You know, I just didn't do this one.
Yeah. A and B are the same.
So, work, I guess.
I just said,
There you go.
watch a car go truck.
Now, is one car going to be going faster? Yeah.
Further.
Smaller mass.
The one with the smaller mass has to be going faster, but with the same force, it's going to undergo a larger acceleration. So you're going to end up, though, at the same distance. Let's see that again.
Ow, I hit my funny bone.
That's funny. Okay, when you get to question number 14, you're going to get a lot of the same answers. So basically what's happening on 14, you're taking this train from rest, you're speeding it up. So if you look at like a kinetic energy graph, so here's your kinetic energy. You're starting it from rest, you're going to speed it up to some big value, I mean a big value, and then basically you're going to hit the brakes and then you're going to bring it back to 0. So you're going to start at 0 You're going to increase the kinetic energy, and then you're going to take that kinetic energy from here back to 0. So that's why you're going to get a lot of the same answers. They're not all the same answers, but a lot of them are going to be the same.
On 15, what's the ish?
For what?
For the distance.
I don't remember right offhand. It's not very far.
Not like maybe
What?
Like
60-ish
perhaps when you might
meters.
retire?
Oh, no, I did not get
Yeah.
Yeah, I think around there, yeah.
Around the retirement age?
I think, let me see, make sure I know which one it is.
What? What is he talking about?
On 60-ish word.
Yeah, it's a pretty big number.
Okay.
Alright, and can you give an explanation again as to 1C?
What's 1C?
It's why does the
Here, like,
velocity of the ball at the bottom
Okay.
change the same as if it was dropped
This is
straight
going to play out largely today throughout the whole lesson. So if you look at what we did yesterday, right, we lifted the tank up here. Okay? And Hank was going to swing down. So when I was holding Hank up here, what's the only type of energy that it had?
potential?
Okay? This was just up, right? So if you think of this in terms of a container, so when it was up here, you had a certain amount of up. I was holding him, this is all we had was up. As soon as I let go of him, he began to move. So then we started to create kinetic energy, right? So let's say this was, I'm just going to make up a number, 4 joules. So if this is 4 joules, as he falls, this height decreases, okay? It's falling. So as the height decreases, my UG becomes less. That has to go somewhere. So imagine this is like a siphon, where I'm siphoning energy from the UG and I'm moving it into the kinetic. So when it hits the bottom here, I don't have any UG, but now my kinetic energy is filled up to 4. Okay? Now, that's independent of the path. If I just lift Hank up to that same height and drop him, I still only start with this much UG. That's it. Which means I can only have that much kinetic energy, which means I can only have that much velocity. Now, the times are completely different. This is going to take a lot longer than if I just drop it. This average acceleration is going to be a lot less than this is because it's swinging in an arc. But at the end, I still end up here with the same velocity as if I just dropped it.
Okay.
Okay? Because if I only start with so much potential energy, I can only have so much kinetic energy. Okay, it's like I'm going to go from here to Chicago. Or I can go from here to St. Louis to Chicago. Okay? Or I can get a direct flight. No matter what, I still end up in Chicago. Shout out to the countries.
We don't go through
Huh?
We go through Des Moines.
Oh, okay.
And then
Des Moines. Nice town. Yes?
Could you clarify on how
To
many,
clarify.
how many are the same on number 14?
Huh?
Could you clarify how many are the same on number 14?
At least 4.
Okay.
changes energy, so if we think
At least 4.
right?
Now, the signs might be different. Okay?
Yeah,
The
the
value.
signs might be final, which is 0 minus your initial.
So, like, what do you have for number 1? Let's make sure number 1's right.
Divided by
Like part A?
Yeah.
the newtons.
2.5 times 10 to the 8th.
Beautiful.
Yeah?
Yeah, that's
On which
fine.
one? On which
On-
one?
Was it 15A?
14.
14A? Yeah, 2.50 times 10 to the 8th.
Okay.
Because if that's wrong, everything else is going to be wrong. So then, that becomes equal to a whole bunch of different things. So you're going from 0 to 2.5 times 10 to the 8th, and then eventually you're going to go from 2.5 times 10 to the 8th back to 0.
Okay. So if I have like 2.49,
You just rounded and made it horribly difficult. You went through and did a whole bunch of calculations that you didn't have to do.
Oh.
Well, we
I thought
also
that's
did.
what we.
I literally told
didn't
him this
do
in
that.
Encore. I was like, you don't have to do that.
Yeah,
We
you
did a
did.
whole lot of
The
calculations.
calculations. It's
So
just
extra credit.
No!
Yeah, so you don't even have to grade this since we did all this extra work on this side column right here. I'll just grade it.
3
Yeah,
that
that's what I said. It's just like,
100 out of
it's,
100.
I told you, you're gonna have a lot of the same answers.
Well, I mean, these are very close.
Okay,
I'm turning.
all right. Anything else?
So that's one question.
I think we're golden, Tony boy.
You're golden? Fantastic.
I'm as gold
Bugby,
as
why
the
didn't
paper.
I, Bugby? Grant, why didn't I get your sign yesterday?
Yeah. Yes,
It's in there.
Negative 2.5 times
I
2.
didn't,
Okay.
I didn't get the last half of it. So, I knew, and then you explained it to me, so then I got it. That's the important.
Not even like Staples' bag of M&Ms or anything?
I was actually going to, but then I'll bring it to you tomorrow, actually.
Yeah, alright.
It's probably because you're a Duke fan.
You know, it's the concept, just understanding things, you know, it's not really great.
I wish it was that way. My life would be so much easier.
My life would be a lot easier.
Almost like this.
Everybody's life would be a lot easier, so why don't we just honestly, who's the one setting these
Like,
standards?
in some schools in Italy,
That's what it is,
throughout,
it's all
no,
pass fail.
no.
That's why Italy's not.
I'm gonna go through
So
keep
throughout the
myself
entire
tonight, how to do this
class,
crap.
like if I was teaching, I would take no grade. I'll give you stuff to do.
Right,
I don't
exactly,
grade
like we have
it, we'll go
assignments.
over it.
I got this one done. I think
But
I got
then,
like.
your grade at the end comes down to 10 minutes one-on-one
Johnny's
oral
like,
final.
but they
But-
lost.
And I
She's
can
like, I
ask
get 1 and
you
1.
anything throughout the entire year, and your grade comes down to that 1 10-minute oral final.
Can we get a little note card to write
Nope.
something?
Who, how do you know
You could
that?
have the equation sheet.
That was the one that I was like sitting there like looking at last night.
That's a different way of, got a lot riding on finals.
Yeah, a lot right now. That 10 minutes, ooh,
That's I'm sweating.
yeah,
Wait, what?
yeah. That's
They don't
big-
grade throughout the year, and they have a 10-minute final. Like,
10 minute one-on-one oral final. I can ask you anything throughout the year.
Who
And that
does?
determines your entire
Oh,
grade.
That's how we're taking the final.
Yeah.
That's how we are?
Yeah.
No, in Italy, yeah, in the college.
Yeah. Yes, we're gonna have a 10-minute in this
No,
class.
don't listen to.
No, Eric would take up the
No, because
entire
then you're
10
just gonna
minutes
ask,
just like trying to explain
to
nothing.
me that the Earth orbits around the sun.
And I was like, centripetal force actually.
Okay, so I was reading this
All I
thing.
gotta say is that's.
I was reading it in English and like they were telling, it was like about a car accident or something and it was like saying the centrifugal force like pulled them out. And I like literally circled it several times and I was like, no it's not, this isn't a
They just
thing.
wanted to go in a
Yeah,
straight
that, I
line.
was talking to you about that back there. You read a story about it.
Yeah.
I never got it back though. So.
Yeah, I like made a note, I was like, this is not physics.
I was like, I read that and I was like, what?
Oh, I was watching.
Okay.
I read that story in class.
He looked so
Yeah.
uneducated.
I was watching ESPN the other day, and they're doing sports science, and they were talking about how a guy was decelerating.
Well, I mean, it's a thing.
Okay.
It was like, he was
It was
at like,
ESPN. Come on.
it was like.
Okay, but the
he was
guy's
at
really
13 miles an
smart.
hour, and he decelerated to.
Well, he
3
did
miles.
decelerate,
I'll
that's
videotape
another-
it and show you.
Yeah, I know.
We're just gonna take
They
a
said- Because here's the problem, if you haven't studied physics and you say he accelerated to 3,
People
He doesn't
wouldn't
get
get
it.
it.
people would flip out. Bubba would be on the phone going, yo, stop, you know, dude.
Oh, Bubba, get back in the barrel.
Okay.
You're the one that made up the problem. Don't look at him like
No.
that.
No, he's looking at
No,
Eric.
I'm looking at Doofus.
I don't know what you're talking about.
Bert,
Okay.
does it just make you mad when the little cruise control says decel and it?
Yeah. Because if it said Axel and Axel, people wouldn't know what to do, so. I'm speeding it up and slowing
That's so
down.
true.
What the
Yeah, they would-
I see that. Which one do I put?
Okay.
It does? I haven't even looked at that. I would put tape over it. Dude, this is a mess. They like call me afterwards and they're like, why do you have to do it all like this? It's because
Okay, so let's say this. So what we're going to look at now is how this energy gets conserved within a system.
Call them out.
So let's say that this is 1 kilogram, but pretend it is. So I got a 1 kilogram mass held up to this height, 2 meters, and I'm going to drop it. Okay? So as it falls, what happens to the energy? Brooklyn, what changes happened in the energy? Well?
Dissipates. It goes other places.
Define those other places, like Oz, like Chicago.
Go Cubbies.
Huh?
Shout out to Mills.
Don't go down the thermal route. When it's up here, what's the only type of energy that it has? Right? Now, as it falls, right, what happens to that It changes into kinetic. Okay? That's it. That's all we want. Okay? Don't make it different. So, when you get a problem like this, and initially I'm going to write out all the different types of energy that you could have. So, when you get into a problem like this, here's the big picture. You could have UG, you could have US, which is energy stored in a spring. Okay, we'll get into that later. You could have translational kinetic energy, which is just 1/2 mv squared. You could have rotational kinetic energy, which is when, like a bicycle wheel is spinning, 1/2 I omega squared. So the sum of all of these energies that you start with has to equal the sum of all of these energies when you get done. So that's going to equal UG prime and US prime and KT prime and KR prime. So when you start a problem, okay, this is the big idea, that no matter what happens with this energy, just like momentum, the sum of all of the energies that I had before has to equal the sum of all the energies when I get done. So what we're not going to consider, and this is something that Brooklyn brought up, we're not going to consider any losses of thermal energy. That gets ugly because then it's like, well, how much are we losing? And so we're just going to assume that all of this energy stays within the system. Accept that. It makes your life simpler. Okay? So when this ball is up here, do we have any US?
No.
No, we haven't like loaded it into a launcher and we're going to launch it. Okay, don't have to worry about that. That goes to 0. Is it moving at this point?
Yes. No, at the top, no.
Is it rotating on its axis as I hold it?
No.
No. Okay? So the only type of energy that I have up here is UG. That's it. Nothing else. That's it. Boom. That's it. So at this point, as it falls, okay, is there going to be a spring involved?
No.
No. Okay? It's still not going to rotate, so we don't have to worry about that. So basically, whatever potential energy I have at the top always has to equal the sum of this new potential energy and that kinetic energy. So if I can ever figure out what this number is, then I know what these two numbers together have to add up to. So when in doubt, make a chart and say, okay, basically, I'm only going to have a change in potential and kinetic energy. Okay, that's it. I'm not going to have springs or anything like that. So make a chart and say, okay, here's what I have going. So right now, the only two games I'm going to have to worry about are UG and translational kinetic energy. That's it. That's all I'm going to have to worry about for now. Eventually, you are going to have to worry about springs. Eventually, you're going to have to worry about pendulums. Eventually, you're going to have to worry about rotational kinetic energy. But for today, these are the only two forms of energy that we're going to have to worry about. And then we're going to look at the sum of all of those energies. So we're going to have UG, kinetic, and the sum. If there was a spring involved, I'd put US. If the ball was rolling, I'd put KR. Okay? If it was two electrical charges, I'd put electrical potential energy. But it's not. So this is the only thing I have. Pretty simple. So if I can ever figure out what one of these values is at some point, and if I know the other one is 0, then I know what the sum of all of this thing has to be. So I've got a mass of 1.02 kilograms, height of 2 meters. Do I have enough information to calculate UG?
Yes.
What do I need?
MGH.
MGH. Right? So I can calculate my UG because that's MGH. I got my mass, 1.02 kilograms. I know what G is, and I know my height is 2 meters. So if I take 1.02 kilograms times G times 2 meters, I should get about 20. Right? Okay? So this is 20 joules. Do I have any kinetic energy? Nope. So that means this is going to be 20 joules. So this is my column that's happening at the top. So I have 20 joules of energy. I don't have any kinetic energy, so that means I've got 20. So what that means is that if I start off with 20 joules of energy, at any point along the way, everything has to add up to 20 joules. Okay? That's it. Boom. All we got. Now, we're going to look at a couple of cases. Situation number 1, I want to figure out how much kinetic energy it has just as it strikes the Earth. Okay? What do I want? Just the amount of kinetic energy when it strikes the Earth. So, just at that point, how much UG do I have?
Find the final velocity.
No, no, no. Don't make this difficult. 0. I don't have any height. Right?
Say that again.
Okay.
What you just said.
Just at the point where this ball hits the ground, just at that very instant of contact, what's my value of H?
0.
So I don't have any UG. It doesn't have any potential to fall any further. Okay? So my UG is, so this is going to be at the bottom. So my UG is 0. So how much kinetic energy do I have then? 20 joules.
21.
So that means the sum, oddly enough, still adds up to 20 joules. What was that? Now, at this point, can I find the velocity of the ball at impact? Yes, how?
1/2 mass b squared.
Okay? So I know that kinetic energy equals 1/2 mv squared. True? Do I know my kinetic energy? Do I know my mass? The only thing I don't know is my velocity. So Mr. Rollins, what does that look like solved for velocity?
Square root of 2k divided by 9.
Beautiful. Okay? So in this case, I'm going to take 2 times 20 joules and divide that by a mass of... So somebody run the numbers. Take 40 divided by 1.02 and then take the square root of that.
0.257.
What?
6.26.
How about 6.26?
Alright. I thought it was like 2 times 0.2. Let's get guess.
No, it wasn't. Okay? So, we got this. All right? Nice number. Kind of cool. So, I want to change it up, though. Now, I want you to go back in time. Back in time. And we haven't even studied forces. We haven't studied momentum. We haven't studied anything except acceleration. And I can tell you that I'm going to drop a ball from a height of 2 meters. And I want you to figure out the velocity of impact. What would you use?
280, all that stuff.
That equation?
Yeah.
V squared equals V naught.
That V squared equals V naught squared plus
People who came up with that are legit geniuses.
2AX. Right? So what's my initial velocity?
0.
0. So I get V equals the square root of 2x. So I get 2 times G times 2 meters. Technically everything underneath here is negative. It works out to be positive. So somebody take basically 4 times 9.8 and the square root of that, and you get...
Well, I'll be. That's crazy.
6.26.
Physics is cool.
Okay?
Honestly, I'm thinking
Now, so here's the deal. When I look at this from an energy perspective, all I'm doing is looking at it from a different way to come up with the same answer. I can't have my kinematic equations of v squared equals v naught squared plus 2ax getting a velocity of 6.26. And then I have another branch of physics that deals with energy getting an answer of 6.5. Okay? So I can't have one set of equations getting one velocity under the exact same conditions and another one getting a different velocity. Everything has to be the same. But now, let's look at this. Instead of having a 1 kilogram mass, what if, I swear to God, if I see that phone out again, you're gone. Is that clear?
I'm pulling up my, okay, yeah.
I don't care what you're pulling up.
Okay.
I do the same thing, but I use Hank. Okay?
Do it.
No. No. So Hank's here at 2 kilograms, or about 10 kilograms actually, 2 meters high. So what's going to change here?
Velocity.
No. With just the energy, what's going to change?
Potential.
Yeah, it's going to go up or go down? It's going to go up. I'm going to have a lot more potential energy at the top. So that means I'm going to have a lot more kinetic energy at the bottom. So if he starts with a lot more potential energy and ends with a lot more kinetic energy, should Hank be going faster than the smaller ball when it's dropped?
No, Galileo was smarter than us.
It's the same. Why? Because what's going to change in this calculation? Yeah, I'm going to have a bigger amount of kinetic energy when I land, but I'm dividing by a bigger mass, so I'm going to get the exact same velocity. Okay? Now, go to this idea. When you did this, did I ever give you the mass of the ball? No, because in this equation it doesn't matter. Okay? The mass matters in your kinetic energy equations, but it doesn't matter when you get down to the end and you find that final velocity. Okay? All right. Now, let's look at this. Let's go back to the 1.02 kilogram mass. Still going to fall 2 meters. But now I want to look at what's going to happen when this thing is just crossing the 1 meter mark. Okay, when it just crosses the 1 meter mark. That's what I want to know. So here's the setup. Start this the exact same way. UG, kinetic energy, and the sum. Am I going to still start with 20 joules of energy?
Yes.
Yes, because that's the constant of the system. Now, don't think that every problem has a constant of 20 joules. It changes depending upon the situation. Don't think, oh, the universal energy constant is 20 joules. Oh, that's nice. No, okay? It depends upon what the situation is. But here's what I do know, is that no matter what, everything has to add up to 20 joules. That's what I know for certain. So when I cross the 1 meter mark, what's going to be easier to calculate when I cross the 1 meter mark? The amount of kinetic energy or the amount of potential energy?
Potential.
Potential, because what do I have to have UG? MGH. Velocity, I'd have to have velocity to calculate my kinetic energy. Ooh, that's ugly. Okay? And again, with this MGH, it doesn't matter if this ball is held at 1 meter, if it's falling at 1 meter, it doesn't make any difference. The only thing that determines that UG at that point is the fact that it's at the 1 meter mark. Doesn't matter if it's on the way up, doesn't matter if it's on the way down, does not matter. The only thing that matters is that it's at the 1 meter mark. So I can get UG here because I can take 1.02 kilograms times G times 1 meter, and I'm going to get 10 joules. So that means my kinetic energy then has to be 10 joules.
So even if like the height was like 3, the total height was like 3 meters, where would the 1 meter be? Like if you're trying to find it at 1 meter, would it be from where you dropped it?
No,
From where-
it's the 1 meter is always determined by where you are above the ground. I could drop this thing from 500
And it's
meters.
1 meter above the ground.
Yes, it's always the distance above the ground. It isn't how far it fell.
Okay, it's always, okay.
It's where it is at that point.
Okay, got it.
Don't screw that up.
Oh, it's not, it's in here.
Okay. Now, do I have enough information to calculate the velocity when it crosses the 1 meter mark? Yes. Now, before you step away from the calculator, nobody even breathe on a calculator. Step away from the calculator. Okay? So at this point, let's look at this idea. At this point, I have 10 joules of potential and 10 joules of kinetic, because I'm halfway down. Okay? That's what I've got. So here's the setup. When this ball lands, we said it landed at 6.26 meters per second. Okay? Reasonable. So here's my question. When I cross the 1 meter mark, here's my options for my velocity. Everything else is split in half. So one option is that I'm going half the velocity, and I'm going 3.13 meters per second. Everything else is split in half. I'm going to be going half as fast. I'm going to be at 3.13 meters per second. That's an option. Option number 2, I'm actually going less than 3.13 meters per second because it's picking up speed and it's only falling 1 meter and I'm not going that fast. The other option is that it's actually going faster than 3.13 meters per second because it's accelerating. So those are our 3 options. It's going faster than 3.13 meters per second. It's going exactly 3.13 meters per second. Or it's going less than 3.13 meters per second. So, how many vote that it's going to be going faster than 3.13 meters per second? Okay?
I'll be the odd one.
You're a Duke fan. Okay. So, now just don't pass judgment. How many vote that's going to be going exactly 3.13 meters per second? 1, 2, 3, 4, 5, 6, 7. Okay? Less than 3.13 meters per second. 1, 2, 3, 4, 5, 6, 7. So it's about an even split between 3.13 and less than 3.13. So for those of you that voted less than 3.13, what was your justification?
The kinetic energy is smaller than it was at 2 meters, and so it's going to be less than, so the velocity is going to be smaller.
Okay?
The mass is still the same, so you're divided by the same mass, but you just have less kinetic energy.
And is that anything radical? Okay? So can we solve the argument?
I mean, there's got to be an equation here somewhere.
Mr. Rollins, how do I find velocity if I know my kinetic energy?
The square root of 2k divided by...
Otherwise known as the Rollins equation, right? I like it though. Hey, come on.
So it's just the square root of 2ab.
So I'm going to take 2 times 10 joules and divide it by a mass of 1.02 kilograms and then take the square root of it. So what do you get? 4.43.
No.
So Grant was right?
Yeah,
Dang, we got a dookie.
Grant, you were right.
the Duke fan was right. Okay? But why?
Exponential.
Because it's the same.
Because of science.
Could you assume square root of 2ab? I feel like that'd be a lot easier.
Good. Here's the deal. Does velocity change as a linear function of distance that it fell?
I don't know what it means.
No,
Yeah,
it
you
does
said
not.
that
Square.
so hard.
Okay? Velocity changes as a linear function of time, right? That's why a velocity time graph is a linear slope. What's going to take longer to fall?
What is that?
That sounds like a telephone.
Yeah, it's just something jacked up with the phone.
Hello?
Is that, how do we know
Hello?
that's not
What?
a, maybe that's a fire drill.
Oh, they want me to go to the office.
I think it's like the integral
we
thing.
don't.
They do.
So here's the deal. If this, what's going to take longer to fall? 0 to 1 or 1 to 2?
0 to 1.
Why?
Because it's accelerating, so it moves faster as it falls down.
That's right. So it's going to take a lot less time to travel from 1 to 2 than it does from
0 to 1.
0 to 1. So that's why it's going to be going, it's going to have a higher velocity, 3.13, because velocity changes as a linear function of time, not a linear function of distance. So this is why it's going faster than 3.13 meters per second, because it takes longer to fall that time, that distance, than it does to fall the second distance. Got it? Good. All right. So you can pick any point in here. If I pick 0.5 meters, so here's the deal. If I say if it's 0.5 meters above the ground, when you do the calculation, use 0.5 meters. Don't use 1.5. Okay? Don't use how far it fell. Only use how far it is above the ground. Yes, Ms. Treadway?
So what if you're dropping something into like a hole that's like drilled into the ground and it's below ground level? Like what?
Then it's just all about reference. Okay? So like if I stand on top of this table, right, and I just let it fall to the table versus standing on the floor and letting it fall to the floor, it's the same idea.
I can't get a good picture of that. Can you show me?
Stand on the table.
Can you just visually?
I have faith in you that you can pull that off. Okay. Now, what would happen if I reverse the process, take the 1.02 kilogram mass, and I throw it up with an initial velocity of, let's say, I don't know, 10 meters per second. So I'm going to take this, I'm going to throw it up from a height of 10 meters per second, or with a velocity of 10 meters per second, not height, velocity of 10 meters per second. So, what's the only type of energy that I have? Kinetic energy. Okay? Because it's right here, I'm going to throw this thing up in the air at 10 meters per second.
Well, don't you have
No. I'm assuming the point that I let go of it is my reference point.
Oh,
I'm just
okay.
going to define that as 0.
Well,
Now, if I was standing on top of the building, then I would have both. Okay?
Okay.
So,
Why does that matter?
You just messed.
No. As long as it goes from here and I catch it back at the same point, it doesn't make any difference. As long as it returns
it's
back.
landing on the same. It's landing.
Yeah, I'm going to have it come back here. But now if I do this, right, and then have it fall all the way down, that's a completely different story. Okay, so as long as it returns back to the same point, we're going to assume that the only thing it has is kinetic energy.
So are we saying potential is at the top when it's at not, I don't know what, changing direction? Before we're changing direction.
So, as it goes up, okay, so visualize this. You have two containers. You have an UG container and you have a kinetic energy container. So, at the beginning, what's the only thing that you have? Kinetic energy. So this is full and this is empty. As it goes up, the kinetic energy gets smaller because you're storing potential energy. And it's slowing down because it's accelerating. So therefore, you're also losing kinetic energy. So, can I figure out how much kinetic energy I have?
Yeah.
1/2 mv squared, right? So that kinetic energy is going to be 1/2 mv squared. So, somebody take 1/2 times 1.02
51.
times 10 squared, you get what, 51? Okay. So I have 51 joules of kinetic energy. So here's the setup. Lay this out, set up a chart, and go, okay, at the beginning, I'm going to have UG, I'm going to have kinetic, and then I'm going to have the sum. At the beginning, how much UG do I have?
0.
0. I have 51 joules of kinetic energy. That means the sum is going to be 51 joules.
I bet you're going to make us do this on our homework assignments and tests. So you're
Yeah, that's why he's teaching it to
I
us.
noticed it yesterday.
like the charts.
Yeah. Why do you think I'm going to do this?
Well, you're not going to make us draw a picture for everyone.
Well, he does tell.
Now, you don't have to do this.
But then you're not going to.
No. No.
Oh, so we don't have to.
You don't have to.
Oh, that's what I was asking.
But if you don't, here's what happens on the test. The kids that don't do this, miss it. The kids that do this have a much smaller chance of missing. Because these are the simple ones, and they're just going to get more and more complex, because eventually we're going to have springs and pendulums, and
So then you're going to have to have everything.
yeah. So if you embrace this idea now,
Embrace it. That's a good way to put it. If you embrace, I like that.
Ready to take
now,
L.
when you get to the top, how much kinetic energy am I going to have?
0.
0. Why do you not have any kinetic energy at the top?
Because you've run out.
The velocity goes to
0.
because you're changing. It also has no movement, but as Mr. Rollins said, what has happened to all of this kinetic energy?
It's moved to the potential.
It's all moved into the potential column. So this now becomes 51 joules. This becomes 0. This is still 51 joules. Now, Mr. Taylor, do I have enough information here to calculate the maximum height of the ball?
Yes.
Yes. Do I know my UG? What does my UG equal?
No.
No!
How do you calculate UG?
That is the gravity times height.
Yes, MGH.
Yeah.
So, what I can do is, I can set this 51 joules equal to MGH. Right?
Keep asking.
Like G is always
So hard.
True? So if I divide by mg, I can get my height.
Yeah. You're deep.
Okay? Makes sense?
Makes sense.
So somebody take 51 and divide it by 10, you should get 5.1.
Yeah, I think I got 5.1.
So this ceiling is about 2.5, so it would go about twice as high as this ceiling. Okay? Go with this. Now, if you wanted to circumvent this and just go old school and go v squared equals v naught squared plus 2ad, there you go. Now, you can do the same thing. So it goes up to a height of 5.1. I could say, okay, when it crosses the 2 meter mark, what's its potential energy and kinetic energy? Start with the UG because that's going to be MGH. Find that, subtract that from 51, use that to find anything
You're
else.
always going to have your MGH.
Okay? You'll always have your MGH. You'll always have your UG.
Your UG's always going to be there for you.
As long as you know the height.
No matter what, it's always technically going to be there though.
Yes.
Even if it's down to 0, it's just always going to be
Yeah. Now, let's change up the situation a little bit. Now, visualize this. I'm standing on top of a building, and instead of just dropping it, I'm going to throw it down. I'm not going to drop it. I'm going to throw it. So, if I throw it down, standing on top of a building, what types of energy do I have?
Spring. Us.
Both.
Okay, so I could have us, I could have UG,
Isn't that like?
I could have KT, and I could have KR.
Right?
That's it.
You got
You got us.
and you got KT.
Like they're going
There's no, where do you get a spring?
Because you're like cocking it back. You're like, oh, but it's in the spring.
That's not
right?
the
Because it's
spring.
in on the
My arms are-
We haven't used it yet, so we must be using
You got
it
you got KT and you got KR. I promise you, if you throw an object, it's gonna have some rotational.
Okay, that's not, we won't.
No, like it rolls off the fingers. Just.
You're throwing a knuckleball.
Your fingers.
Oh.
No.
Okay? Now, when it hits the ground, down here, what's the only thing it's going to have?
Kinetic.
K.
Wait.
So we're going to call this KT prime. Now, if I just drop it, UG equals KT prime. Now, an interesting thing happens. If I just drop it, okay, let's not worry about the throw. Let's just assume that I just drop it like this. UG is going to equal what? MG H. This is going to be 1/2. What's going to have it as a mass?
Whoa. Wow, no, why'd you do that?
It's going to cancel out. So a lot of these problems, you'll see that I won't give you the mass. Why?
Because it.
Because you can drop it out of the equation.
Why'd you do that?
Okay? Because you can drop it
Alright,
out.
so
Now, if I throw it, what's the only thing that changes on the left side?
MGH.
Acceleration. You just have a V
On the
I
left
am
side.
going to have an acceleration. If I throw it down, okay, as opposed to just dropping it, it's now also going to have what?
KT.
Some kinetic energy,
So it's times 2.
right? But
So-
now we have two different velocities. We have a V here and a V here.
Oh, crossing.
Which one is the V naught?
Be not musician, so I'm gonna imagine
On the left.
side.
Far left.
So here's what I've got. 1/2 M V naught squared plus MGH equals.
No, plus GH.
How does it cancel them out
Still
yet?
count in.
Wait, you can't take
I am
They're
so
in out.
confused.
Okay, here's what I've got. I'm going to throw it down, right?
Apparently you're keeping
So I'm going to have a certain amount of kinetic energy.
Factor it out.
True?
Cancel it.
Yes.
And I'm going to have potential energy because it's still above the Earth.
Yes.
Oh,
Then
factor
when
out
it
the end.
lands, it's all going to have kinetic.
Right.
So these two values together have to add up to,
So can you factor out the ends?
oh yeah, you can do a whole bunch.
Are we talking about?
Okay, you can do a whole bunch of things with
We're
this.
talking about ends.
Yeah, yeah, you can.
Ends, baby,
Yeah.
ends.
M's gone, baby.
Yeah, we're talking about ends.
Yeah.
Can we talk about G's?
We're talking about,
No,
talking about
no, we can't talk about it.
We're talking about ends.
Okay, so just keep this in mind, kind of file that in the back of your knowledge.
You got clean, I got.
Just say.
Right.
Now,
I got clean, I got nice, I got.
oh,
Clean, I got rice. I got needles and pumps, I got clean, I got rice.
let's say that I have two objects.
I don't cheat on the dice.
Hank the golf ball,
Hit on the spot.
Hank golf ball.
Hank the golf, or excuse me, Hank the bowling ball, and Gary the golf ball. Okay, so I got Hank and I got Gary, all right? I have them at the same height, okay? I have them at the same height. If I drop them, are they both going to land with the same amount of kinetic energy?
No.
Why?
Because the
That's
mass
what
is
I
Has the
bigger.
same velocity.
Yeah, Hank's going to have a lot more.
Mass.
Are they going to land with the same velocity?
Yes.
Yeah.
Yes,
Galileo says so.
because Hank starts off with a lot more
Wait. There's.
inertia and a lot more potential energy than Gary does, right?
Gary?
So Gary has less potential energy than Hank does. But when they land, they both have the same velocity, but they don't have the same kinetic energy because Hank still has more mass, right? So let's say, for the sake of argument, that they both fall for 1 second. Okay, which means you'd have to have them from a height of about 4.9 meters. Okay, it's about twice the size of C. So they both fall for 1 second. And to make this graph easy, let's just say they're both going down as positive. So here's the deal. So here we'll talk about Hank first. Let's say that Hank has a mass of 10 kilograms, right? And at the end of 1 second, Hank's going to be going how fast? We're going to let him fall for 1 second.
9.8.
9.8 meters per second, right? Because if something falls for 1 second at an acceleration of 9.8 meters per second squared, right? So if I take Hank at the end of 1 second and multiply that by 9.8 meters per second, I get 98 Newton seconds, right? That's the momentum. True? That's the momentum of Hank at the end of 1 second.
Yes.
Right? So I could come out here to 1 second. Here's 100, and I could draw this line.
Wait, what is that?
So do you think momentum changes as a linear function of time?
Oh, yeah.
Yes. Why?
Change in momentum equals mass B minus B naught.
You're making this difficult. It does equal that, but that's not the point.
Because velocity.
Does velocity change as a linear function of time?
Yeah.
So therefore, momentum has to change as a linear function of time.
What's momentum?
Mass times velocity.
Because P equals MB. No, what's, you said, okay. Hey, it's okay. That's the question.
It's okay.
It's all right.
All right.
Okay.
Now, so I'm out here at 98 Newton seconds because Hank was going, if he falls for 1 second, he's going to travel at 9.8 meters per second. He has a mass of 10 kilograms. Now, Gary is also going to fall for 1 second. Right? So how fast is Gary moving at the end of 1 second? 9.8 meters per second, right? Okay? So let's say that Gary has a mass of 0.1 kilograms. So if we take 0.1 times 9.8 meters per second, I get 0.8 Newton seconds. So Gary is going to end up out here like this. Okay?
Okay, so what's the triangle that's formed?
There is no triangle.
Yep.
Well, there is, but I don't care about that for now. Okay? So, could I find the slope of this line?
Yes.
Yeah.
You know the slope of it, don't you?
I don't know. Well, I got 98 Newton seconds.
It's 98. Yeah.
It's 98 what?
Newtons.
Oh, 98 newtons. So if I take 98 Newton seconds.
Why is it not 98 newtons?
Because
and
Newton's.
divide that by 1 second, the seconds cancel out, and I get 98
I'm just kidding, Ken.
newtons. So what does the 98 newtons represent? The force that's acting on Hank. Now, so the slope of a momentum time graph gives you force. Now, look at Gary. Gary's out here at 0.98. If I take 0.98 and find that slope, I get 0.98 Newton seconds, right? I divide that by 1 second, I get 0.98 newtons, which is the force that's acting on Gary. So, even though they're going to end up with the same velocities, okay, they're not going to end up with the same momentum. But the slope of a momentum time graph gives you the force. Okay? Got it? Good? All right. So,
I'm done.
all right. So, let me kind of take you through some of these problems. So, on number 4, you got an arc proposed back of 0.3 kilogram, average force of 201 newtons is exerted, draw force distance graph. Okay? So, here's why I say it's an average force. If you've ever pulled back a bowstring, the first, couple of centimeters pull is pretty easy. As you get closer to the end, it's harder and harder and harder to pull it. So that's why I say, on average, you're going to exert 201 newtons of force. So as you pull that back, what are you storing? Potential energy. When you let go of it, that potential energy changes into kinetic energy. Keep that in mind. Now, when you get down to number 5, so derive an equation that allows you to determine the final velocity of a ball that is thrown downward from the top of the building. Show every step, leaving nothing to chance. So in other words, when you get done, you should have an equation that says V equals blah. Okay?
Tell us.
No. No. But I basically worked the entire problem up there. All you'd have to do is solve it if you had it written down. So then on number 6, and by the way, when you get done, if you do number 5 right, you should have an equation that's very recognizable if you do it right. Okay? If you do it right, you should get a very recognizable equation. Now, when you get to number 8, I have given you the net upward force. You don't have to subtract out the weight of the rocket. I already did that for you.
Thank you.
So that is the net force. That's what you use in the force calculations of work. Don't make it difficult. Okay? That is the number. Now, when you get to number 9, you've got Timmy with a mass of 100 kilograms, Susie with a mass of 60, facing each other, they push off. This starts with momentum, it also ends up with energy. Okay, so I'm kind of going old school, working some momentum back into the situation on number 9. Okay, now you're on your own.